All right, then I would like to welcome everyone to this webinar number 4 in this discussion series on tipping elements, irreversibility and abrupt changes in the Earth system. I'm Heiko Gölzer from the Bjerknes Center in Bergen, Norway, and I'm here as a member of the WCRP Lighthouse activity Safe Landing Climates that I will say a little bit more about in a minute. So the goal of this discussion series is to advance our knowledge on tipping elements, support efforts to increase consistency in treatment of tipping elements in the scientific community, to develop a research agenda, and to design joint experiments and ideas for a tipping element model intercomparison project. The first webinar in this series in September last year provided an overview of tipping elements and climate extremes. And since then, we have had 2 events on Amazon rainforest and permafrost. After the event today, we will continue also in February and the rest of the year with further discussions, first on ocean and the Atlantic Maritime Overturning Circulation, and then you can check the program, what comes after that. You can register for the upcoming events with a link that I hope it will be posted now in the chat box. You can also look back to the events in the past on the WCRP YouTube channel. So the focus of today is ice sheets and their tipping points, and we will hear presentations that will address the future behavior of the 2 ice sheets that we have on our planet today, which is the Greenland ice sheet and the Antarctic ice sheet. And these ice sheets are quite different in their climatic settings and evolution, and consequently also in their suggesting tipping behavior. Before going to the introduction of the speaker, I will give a short overview of the 3 organizations that have initiated this discussion series. And there we have first the Earth Commission, which is a global team of scientists with the mission to define a safe and just corridor for people and planet. And this will inform setting targets for a stable, safe planet, and will help us in developing and understanding pathways that are compatible with these targets. So that was one, the Earth Commission. Second is the Analysis, Integration and Modeling of the Earth System project called AIMS. And this is a global research network of future Earth comprised of Earth system scientists and scholars that seek to develop interdisciplinary ways to understand the complexity of the natural world and its interactions with human activities. And the third organization is the Safe Landing Climate Lighthouse activity of the World Climate Research Program, which explores routes to safe landing spaces for human and natural systems. It will explore future pathways that avoid dangerous climate change, while at the same time contributing to the United Nations Sustainable Development Goals. So these organizations have put together this series. And yes, now I want to pass the word to our other chair today, which is Hanna Liddy.
Hi, everybody, and a warm welcome from my side as well. It's great to see everybody here. My name is Hanna Liddy, and I am the Executive Officer for AIMS. I'm based at Columbia University and at NASAGS here in New York City. Before I introduce our first speaker, I'll provide an overview of today's events and modes for interaction. So both of our speakers will present before the Q&A session. However, during their talks, feel free to pose questions and indicate to whom your question is directed to in the Q&A feature, which is located at the bottom of the Zoom window. And everyone can upvote questions that you would like to hear answered, and we'll make sure to stay aware of that. We will then get to these questions in the discussion session following the presentations. We also have a number of experts in our audience today, and so we want to encourage a lot of interaction. And so to facilitate that, we have set up an interactive Miro board, which is like a virtual whiteboard that can be used to leave comments or respond to prompts that we've provided on the board. And that link can be accessed through the chat box. The Miro board will be kept open throughout the week, so for any ongoing discussion can continue there. And following the event today, we will also post the recording of the talks on the Tipping Point series Confetti webpage, which is, I think, where many of you signed up. So it will be accessible in the future. So Now, with housekeeping aside, it is my pleasure to introduce our first speaker, Professor Sophie Nowicki. Sophie is an Empire Innovation Professor in the Department of Geology and Renew faculty at the University of Buffalo here in the US. She holds a PhD in theoretical glaciology from University College London in the UK. Her research focuses on the Greenland and Antarctic ice sheets, their connections to the Earth's climate system, and their impact on sea level. Sophie is a co-lead of the Ice Sheet Intercomparison project for CMIP, ISMIP 6, and is the lead author on the 6th IPCC Assessment Report chapter on ocean cryosphere and sea level change. Sophie will be providing an overview of centennial projections from ISMIP, the Antarctic Buttressing Model Intercomparison Project ABUMIP, and we'll also provide updates from the IPCC AR6 Working Group 1 report, which was recently released. We're so happy to have such an expert with us today. So thank you, Sophie, for being here, and the floor is yours.
Thank you so much for inviting me to talk, and I will share my screen and my presentation right now. It was a lovely introduction, Anna. Yes, my name is Sophie Nowicki, and I like to, in this kind of presentation, have a picture of my grandmother, as you see here, with my children. And as you can see, my children are super excited, right? It's super nice. They're about to jump for joy. You can make your wild guess. They love going to the sea. So does my grandmother. We all have this in common, and they know that sea level is rising. But the reason they are, because of my work, because I talk to them about my work, right, as a good mom. And so the reason they're super excited is that we're about to eat the birthday cake of my grandmother, and you can see the number is 105. So the point of this picture is that the time difference, the age difference between my grandmother and my kids in that picture is about 100 years. And so that's really a driver for my work right now. I am really kind of, my driver is to understand what is a future that my children will face should they have the same lifetime of 100 years. That might seem so far away, but in my family, it's really a few generations. So then let's look at some plots and some science. Throughout my grandmother's lifetime, the temperatures have increased, and so has sea level. But then throughout my children's lifetime, the temperature have increased much, much faster, and so has also the sea level change. And so really that's, again, the driver of my work. What is the future sea level that we should face and get ready as a society for the next 100 years time frame? I was fortunate to be an IPCC author of the recent assessment report. And so most of my presentation is actually based on what the findings of this report, because I think that this is going to help you in the future as you define your TPMIP, what questions to ask. At least you have the correct baseline. A main finding that the assessment report did is that the Greenland ice sheet will continue to lose mass throughout the century under all emission scenario. And this is virtually certain. And as you can see is that the warmer and the higher the emission scenarios in the SSPs in red generally results to a higher sea level. And a question that we get asked a lot when we were writing the report and ever since is how do those numbers compare to the SROCs in the previous assessment, the AR5? And so what we write in the text is that for the low emission scenarios, the contribution of the Greenland and Antarctica sheet to 2100 will likely be, a 0.01 to 0.1 meters on the low emission scenario, versus this different number for IPCC AR5 and as well. And you can read those numbers, so I will just not go and blabber around. But the key message is that compared to the previous assessment report, the AR6 has a slightly narrower projecting range, but the median is more or less the same for both of those scenarios. So to keep two takeaway message. The numbers of AR6 are fairly similar in terms of the median compared to previous assessment. You know for sure that the Greenland ice sheet will continue to lose mass at a higher number with the higher scenarios. Okay, well, what is behind these projections, right? I mean, you could read the whole report, but I thought it would be helpful to kind of give you some of that. Well, I like to kind of introduce this, that behind those AR6 projections, you have a zoo of ice sheet model. That's maybe a bit unfair, but the takeaway message is that there is right now internationally a lot of ice sheet models. They each are different in terms of their physics, in terms of the input that they do, in terms of how they initialize. And basically with ISMIP 6, anyone who would take part into the protocol that we had designed could take part. And so the ISMIP 6 projections really capture right now the whole range of current ice sheet models in the world. So we have a zoo of ice sheet model that is forced by selected CMIP models, because basically for an ice sheet model to make projections, even under 100 years time scale, it takes a very, very long time. So you cannot do all of the future scenarios that the climate models give you. You have to kind of down select. And so that's what we did with ISMIP 6. We spent a lot of time trying to basically select climate models that could be used as forcing for both for the atmosphere and the ocean in order to do a projection. So, and we have tons of papers on how we selected them, what were the requirements, how we derive the forcing, that we spend a lot of time doing this. So behind the ISMIP 6 projections, you have a zoo of ice sheet models forced by selected CMIP models. But then of course, the issue is that, you know, we still want to have more simulation, but we really want to kind of trying to sample the whole uncertainty. And so what we did then is that we emulated them. And this is the paper by Thames and Edwards et al. That basically learned from these ISMIP 6 simulations that we had done, and did an emulation in order to cover much more scenarios and much more climate models. So that's what ISMIP 6 gave you. But the AR6 is not only that. It's not only ISMIP 6, right? You also have, because you have to assess all of the literature. And so you also have coupled ice sheet climate model simulations, for example, if you look at the tables in chapter 9. And we described the pros and cons about each of those type of modeling. So because, for example, the nice thing about an ice sheet coupled to a climate model is that you can have some feedbacks, but then maybe there might be issues about forcing to the ocean. So we talk about all of that. We also put into context, you know, all the literature, of course. And so there is a very important, there are statements in addition to the table, and this is one that I like very much, which is that these projections, as well as those of AR5 and AR6, are lower than the study of Ashland and et al., all the range from SEG, which is expert solicitation, contributing to the deep uncertainty in projected sea level. So this deep uncertainty in projected sea level is something that we talk a lot in the report, and I will continue. I will go a bit more into this very soon. So for the Antarctic ice sheets, same story. What do we find? What are our findings as part of the assessed literature? The Antarctic ice sheet will continue to lose mass throughout this century under all emission scenario. It is likely. What we do find compared to the previous assessment reports, well, for the low emission scenarios, for the SSP 1.26, we have a higher median in terms of projections and a higher upper end. And then for the high emission scenarios, the SSP 58.5, we have more or less the same median as previous assessment report, but a higher upper end. How did we get those numbers? Those projections, again, it's like some similar to the Greenland ice sheet. We have a zoo of ice sheet models forced by CMIP models and emulated. That's the ISMIP aspect, which is on that part in lighter blue. But you also assess all of the current literature. And so you also have this other effort called LARMIP, which is linear response function for Antarctica. And so we use that to recombine those those simulations. That's also a MIP, so therefore it's also many ice sheet models taking part into the setup. It is a lot of the models have a similar between the two MIPs, so there is some similarities. Just the way that the forcing are done are very different, and some of the concept. However, LARMIP is only a response to the basal to the ocean for Antarctica, and so for in order to make it comparable to the IPCC projection, or to make it because basically the future of the ice sheets is going to be a combination about how much the ocean is going to warm, so this is the ocean aspect, but also how much the atmosphere is going to change, and that will be how much surface mass balance or snowfall, for example, would fall on the ice sheets. So for the assessment report of the IPCC, we had to basically add this component of surface mass balance, the snowfall that could cause the ice sheet to grow, for example, to those LARMIP estimate, and that's what we did using a method very similar to what had been done in previous assessment report AR5. And so again, another way to look at those numbers in the tables, because and in the text, because it's you have to, again, as I've said multiple times, it's going to be IPCC projections, LARMIP projections, and more. So we assess whatever there is currently in the literature at that time. And so it's just putting again those numbers for the medium confidence processes. It's basically what the numbers that are going to be quoted as in the report. And those are the numbers we've just seen before, right? But we've also mentioned that there is there's this possibility of a higher sea level rise, and that comes from multiple lines of evidence. One of it being the marine ice cliff instability and the work that's been published, and some of those simulations, and the projections. You also have, just like for Greenland, we also said, it could be higher sea level due to the expert elicitation, so that gives those numbers. And we also have, and when we talk into the report in the box 9.4, which has a high-end storyline. So we have a very long box about, what could happen, what needs to happen, or what could possibly happen to have higher sea level rise. Why can't we rule out higher sea level rise than this likely range, which is in blue? Then we talk in that box about this ABUMIP, which is circled here in yellow. ABUMIP is very interesting because it basically acknowledged the fact that we don't really know, and that there is still some unknowns about what could cause the collapse of the ice shelves. But we do know that if the ice shelves collapse, that you could result into the ice sheet retreating far inland and leading to a very high sea level. And that's what this ABUMIP shows, basically, where in green, in all of those regions, is wherever in the end, the ice sheet has retreated and basically is now lost. So it's something that TIPMIP eventually may want to kind of revisit in terms of understanding what could happen if you don't really know the forcing that could lead to a collapse of the ice shelves. So that's that aspect. I just want to, for the sake of time, continue moving on, but we do continue on saying in the report that there is this uncertainty that can really happen due to the possible evolution of the Antarctic ice sheets for this century, right? And so it's just related to, as I've shown with ABUMIP, this collapse of the ice shelf, so the marine ice sheet instability, or you could also have this marine ice cliff instability. And if you have those instabilities, then for the year, even for year 2100, you could have a very sea level rise that is much higher than what we call those medium confidence projections. So this is that little dotted line is basically what are much higher sea level that could happen if you have processes that leads to those instabilities. And of course, to 2100 to 2300, the more you project in time, the more those numbers become higher. So the AR6 also defines tipping points, irreversibility, climate change, low likelihood, and high impact outcome, which could be of relevance to the rest of this discussion today. And I thought it would be nice to remind ourselves about what it is. So a tipping point is a critical threshold beyond which a system reorganizes, often abruptly and or irreversibility. The irreversibility aspect, it's like a perturbed state of a dynamic system is defined as irreversible for a given time scale if the recovery from this state is due to a natural process takes substantial time compared to the time scale of interest, and so that's also a tipping point. The abrupt change is a change in the system that is substantially faster than the typical rate of the change in its history, whereas the low likelihood, high impact outcomes, those are probabilities of occurrence that is low or not well known, but the potential impact on society and ecosystem would be high. And so really go and look in the IPCC for those definitions. And for the ice sheet, we do, so there is a table that is a very amazing table, the table 4.10, and I've only basically picked out the 2 lines that are relevant to the ice sheets. So for the Greenland ice sheet, the answer is like, there are questions. Is there potential for abrupt climate change? And it was assessed that no, the changes that you would see for the Greenland ice sheets will not be abrupt. Is it possible for it to be irreversible? Is it irreversible? And so the next, for the Greenland ice sheets, the answer is, yeah, it can be irreversible for millennia with high confidence. How would the projected change for the 21st century under continental warming? It's going to be virtually certain that all all scenarios. And how does it compare to previous assessment? Well, for AR6, we provide more lines of evidence than SROCs. For the West Atlantic ice sheet, it's a different story. Yes, you have more potential for abrupt climate change with high confidence. That is, if you do have this kind of religion collapse. It is irreversible for decades to millennia with high confidence. We find that it will likely lose mass under all scenarios for the 21st centuries. But there is really deep uncertainty in what those numbers are. And those uncertainty are really linked to how much the temperature rises. For projections above 3 degrees, it becomes really deeply uncertain. And how does it compare to previous assessment report? We've added this question about the uncertainty. And that plot below is just to kind of remind ourselves that, ice sheets can take a very long time to grow because they grow from snowfall, but they can lose ice and collapse very fast. And so especially when they become destabilized. And so what are the type of destabilizations that could happen? Ricarda will go into more of that. But for Greenland, for example, one of the dominant one would be melting driven by air temperature, which is what those plots are. So melting by the atmosphere. Whereas for Antarctica, a good destabilization mechanism is basically driven by the ocean. To the report also put into context what has happened into the past. And so when we look at the paleo, the information that we have from the paleo, what the key message that we take away is that you can have a sustained warming. That's basically where we kind of talk about this difference in temperature. And so between 3 and 5 degrees, a near complete loss of the Greenland ice sheets and complete loss of the West Atlantic ice sheet is projected to occur irreversibly over multiple millennia with medium confidence. And so that's really this kind of cut-on point about 3 degrees is something that we highlight because below 3 degrees, yes, the ice sheets will likely lose a lot of mass, but they might not collapse altogether, or they might not be a near total loss. So just to wrap up then, what was the IPCC AR6? We provided new lines of evidence to support previous reports, conclusions, and we provided an improved assessment of the rate of change. And so we also provided a high warming storyline, those that are linked with a global temperature that are much higher. And so even though those temperatures might be unlikely, therefore, in a way, the potential sea level linked to it might be also very low, they cannot be ruled out. And that's something very new for these AR6 projection, this inclusion about those low confidence projections that give very high sea level. And so my third point is that it is virtually certain that the global sea level rise will continue to rise throughout this century and beyond. But there is really deep uncertainty in ice sheet melt rates and global sea level rise at global warming above 3 degrees. So the final point with that slide and that image is that, of course, ever since AR6 was published, there has been continued research where the scientists will continue researching. And so there's tons of publications, there is new research coming out that we couldn't take into account into the report. So this is an example of IPCC 6 experiment extended to 2300 by one group and how Antarctica will lose mass. But there is also new research on tipping points that we couldn't include because they were not there when we wrote the report. So I'm really looking forward to this new research coming out and to what IPCC will produce. And so with this, I wanted to thank all of the IPCC 6 participants, which are in those pictures, and of course, the Chapter 9 co-authors. And so I will stop screen sharing.
Great. Thank you very much, Sophie. Really super nice overview of AR6 and of the underlying simulations. If you have any questions in the audience, please put them in the Q&A box. There's already some accumulating there, and we will move on to the next speaker. And Sophie, if you want, you can already try to answer some of them. If you want, you can also listen to what Ricarda has to say, of course. Yeah, please continue using the Q&A box, use the Miro for things you want to discuss or bring up outside of that. And now it is my pleasure to introduce to you Professor Ricarda Winkelmann. Ricarda is a professor at Potsdam Institute for Climate Impact Research and University of Potsdam. She is a co-chair of Working Group 1 of the Earth Commission and leads the IPCC Intercomparison project that we have heard some about already. She is trained as a mathematician and theoretical physicist in Germany and in the United States. And Ricarda received her PhD with distinction from the Potsdam Institute for Climate Impact Research and was a visiting researcher at the Carnegie Institution for Science in Stanford before returning to Germany as a professor of climate system analysis. Ricarda has received numerous awards for her work, including being named Young Scientist of the Year by Academics Inside Publishing Group. Her research at the Potsdam Institute is on ice dynamics in Greenland and Antarctica, future sea level rise, and last but not least, tipping elements in the Earth's system. So today, Ricarda will be addressing the longer timescales of ice sheet dynamics in Antarctica and Greenland. And with this, please take it away, Ricarda.
Yeah, thank you so much, Heiko, for the very kind introduction. I'm complementing Sophie's excellent overview of our knowledge of sea level projections within this century. I now want to take a deep dive into some of the more long-term risks when it comes to tipping points in Greenland and Antarctica. And I want to start off by reminding ourselves what a special period of time we actually live in. And there's almost no graph that captures this as well as this one, at least for my understanding. What you see here, it's the temperature change from the last glacial maximum, so the last ice age, till today. And there are two very striking features here. One of them is that the Holocene, so the time during which modern civilizations have developed and thrived, that was given by a very stable general climate, so a stable global mean temperature. And this happened for the past few thousand years. And then the second thing is that the difference between an ice age and a warm age, such as the one that we live in today, that's roughly 3 to 4 degrees of global mean temperature difference. So it's really not that much. And what we're facing right now is actually the same temperature difference or even higher temperature differences, but in much, much shorter timescales. So this really means that we are now deep into the Anthropocene and that humans have become a geological force and one of the main drivers in our Earth system. And this, of course, also affects our ice sheets in Greenland and Antarctica. And I just want to remind ourselves what is at stake here. So one of the numbers that we should all remember is the so-called sea level potential for these two ice sheets. That means that if the Greenland ice sheet were to melt down completely and we distributed that meltwater over the global ocean, then sea levels worldwide would be raised by more than 7 meters. For the West Antarctic ice sheet, it's another 5 meters, and for East Antarctica, even the tenfold, so more than 50 meters worth of sea level rise that is currently stored in that vast ice sheet. So these are really sea level giants, and they're constantly moving and changing. And in fact, over the past decades, the ice sheets have both been losing mass, and they have been losing mass at faster and faster rates. One of the main reasons for this mass loss in Greenland is actually through increased melts at the ice sheet surface. And you can see a picture of that here in the background. And not only is the surface melt increasing gradually over Greenland, but there also have been a number of extreme melt events in Greenland, and they have become more and more frequent and also more intense over the past decades. You may remember some of these extreme melts summers, for instance, in 2012, in 2015, and also in 2019, when this was all over the news. And this melting at the ice sheet surface gives rise to a self-reinforcing or positive feedback mechanism. And it works as follows. So we all actually know this from mountain climbing. That is, when we climb down from the peak of the mountain to the valley, then it gets warmer around us. And the same is true also for the ice sheet surface. So if there is a substantial melt at the ice sheet surface and the surface itself is lowered, then that means that it gets warmer at the ice sheet surface and there can be more melt, and so on and so forth. So it's a self-accelerating feedback mechanism called the melt elevation feedback. And this positive or self-accelerating feedback can drive sustained mass loss in Greenland once a critical threshold or a tipping point is crossed. And here you can see an animation of what that might look like. So this means that even without any further warming, the Greenland ice sheet will lose mass substantially and could eventually even become ice-free. Now, of course, this doesn't happen overnight, but as you can see, it can take several hundreds or even thousands of years. But that critical warming level at which it happens, so the tipping point, that could already be crossed in the coming decades. And Sophie already pointed this out, that we find that complete irreversible loss might occur possibly already between 2 and 3 degrees of warming, and almost certainly above 3 degrees, so between 3 and 5 degrees of warming for the Greenland ice sheet on the long term. For Antarctica, the story is slightly different. Again, we've also seen accelerated mass loss from the Antarctic ice sheet over the past decades. And this is especially in the Amundsen and Bellingshausen Sea region here in West Antarctica. And a key driver for the mass loss in Antarctica, though, is not the changes at the ice sheet surface, but rather the melting from below. So where the ice shelves are in contact with warmer ocean waters, we have so-called subshelf melting. And this is one of the main reasons why Antarctica is currently losing mass. So it really is this ice-ocean interaction that is what is most important when it comes to the tipping potential for the Antarctic ice sheet. And you can see all around Antarctica, the ocean temperatures are actually quite different, and they can differ by as much as 2 degrees between areas as the Weddell Sea region here, which is a rather cold Southern Ocean area, and then compared to, for instance, the Bellingshausen and Amundsen Sea region, where we see that accelerated outflow, where it's roughly 2 degrees warmer. So this either ocean warming or inflow of warmer ocean masses into the ice shelf cavities leads to increased subshelf melting. And even though ice shelves do not contribute to sea level rise directly, or almost not directly, they have a really important role for the sea level rise, and that is they have this kind of buffering role. So they almost act as a buffer or a cork in a bottle. So if the ice shelves thin, then that buffering or buttressing effect is reduced, and that means that we can have more outflow from the interior of the ice sheet into the ocean. And that is why subshelf melting and ice shelf thinning are such important processes when it comes to the mass balance and the stability of the Antarctic ice sheet. Now, this subshelf melt can actually give rise to another instability mechanism, or a positive, meaning self-accelerating feedback in Antarctica, and that is the so-called marine ice sheet instability. For the marine ice sheet instability to take place, there are 2 conditions that need to hold. One is that we have, as the name says, a marine ice sheet, meaning an ice sheet that is grounded below sea level, such as in this sketch here. And secondly, the grounding line needs to rest on retrograde sloping bed. The grounding line, that's the line separating the grounded ice sheet from the floating ice shelf extensions. And when we have such a situation, we can have the marine ice sheet instability taking place. That means that with a retreat of the grounding line, for instance, through increased subshelf melting here at the underside of the ice shelves. So once the grounding line retreats slightly, we actually have a thicker ice sheet at the new grounding line position, which can lead to more outflow across the grounding line, and again, and so on and so forth. So it's a self-accelerating feedback that takes place and may only be stopped once the grounding line reaches a prograde sloping bed again. Now, in theory, this is all very clear. We can even show for a flow line situation, so a 2-dimensional ice sheet, we can even mathematically prove that there is such an instability mechanism for these kinds of grounding lines. So positive feedback between the grounding line retreat and the flux across the grounding line. But in reality, the situation is, of course, much more complex because we do have the potential stabilization of grounding lines also on the retrograde sloping beds through ice shelf buttressing, so through this buffering effect of the ice shelves. And all of this gives rise to very complex dynamics. And so does another instability mechanism, and Sophie already mentioned this one, the marine ice cliff instability. And here the idea is that through calving, it can happen that, so through the breaking off of icebergs, it can happen that we get a really steep cliff at the ice front. And if that cliff is then tall enough, and one says that this is roughly around 800 meters of ice thickness, then the stresses at the cliff will exceed the strength of the ice. And that means that that cliff can fail structurally, and this can lead to repeated calving events, giving rise to an instability or positive feedback mechanisms that works something like this, where we have a higher cliff that increases the stresses at the cliff face, that leads to more calving, and so on and so forth. And there's still a lot of uncertainty when it comes to all of these instability mechanisms, and in particular the marine ice cliff instability. And yeah, I'm happy to discuss that also further later on. All of these instability mechanisms together, they will determine the overall stability of the Antarctic ice sheet. And what you see now is a simulation with the parallel ice sheet model showing that we actually have a sequence of tipping points in Antarctica. And you just saw the first one at around 2 degrees of warming that is mainly caused by these processes at the ice-ocean interface and the marine ice sheet instability, leading on the long term to a partial collapse of the West Antarctic ice sheet. And as you see, as the temperature keeps rising, we're now reaching 6 to 8 degrees of warming. There's another major tipping point in East Antarctica. And this time it's actually not through the ice-ocean interaction mainly, but rather through the surface processes. So this is when the surface changes really become dominant, and also the melt elevation feedback that we saw earlier for the Greenland ice sheet can play an important role in determining the long-term stability of the Antarctic ice sheet. We need to think of these kinds of simulations not in terms of projections, but rather in terms of a risk assessment or a stability check of the Antarctic ice sheet. And we can also check in how far these changes are reversible. And what we find is you now see on the right a comparison between the warming state and then cooling down the planet again to see if the Antarctic ice sheet regrows. And what we find is that once lost, parts of the ice sheet actually do not regrow, even if the warming is reversed. And in particular, in West Antarctica, there are large parts that do not regrow to its present day extent until the temperatures are at least 1 degree lower than pre-industrial levels. So I think it's safe to say that ice sheet tipping points are too risky to bet against. And I think one important notion is also that because of these tipping points, it really is our actions today that define the long-term evolution of our global climate, and also, of course, the ice sheets and sea level rise. So we can think of this long-term sea level commitment almost like our ultimate heritage. What you see here is a simulation for a scenario that is actually still compatible with the Paris temperature range of 1.5 to 2 degrees of warming on the long term. But this is the multimillennial sea level rise and the effect it has on the coastlines around the world. And everything you see in purple, those are areas that are submerged in countries where at least 50 million people live on land that is affected by this projected multimillennial sea level rise. And as you can see, this would really hit coastlines around the globe. So from the United States to China, to Bangladesh, and of course, everywhere around the world as well. Here you only see highlighted regions that are very heavily populated. One important question we need to ask ourselves is, could these changes in the ice sheet put other tipping elements at risk as well? And we've seen in this series already a number of other tipping elements. And we've looked into the literature and made a new overview to assess what we know about these critical warming thresholds or tipping points for individual tipping elements in the climate system. And what you can see here is that the ice sheets are only some of the tipping elements in the climate system. And overall, you can see that above 1.5 degrees of warming, that could actually already trigger multiple climate tipping points. So that is the kind of risk that we're facing on the long term. Now, for comparison, on the right here, you see the current warming level, and also what current policies would give us in terms of the warming level. So we're really right in that risk zone when it comes to these tipping elements. And of course, the tipping elements do not exist in solitude, but rather they interact in a very complex manner in the climate system. Here you see just some examples of interactions also between the Greenland and the Antarctic ice sheet, for instance, via the ocean circulation. And we need to further understand how these interactions affect the critical thresholds or tipping points for the individual elements again. So far, we've been doing this using more conceptual approaches or risk analysis, where we can actually propagate the uncertainties not only in the critical temperature thresholds, but also in the interaction strengths between, for instance, the Greenland ice sheet, the ocean circulation, and Antarctica, and also the interaction structure. So what does that network of tipping elements in the climate system really look like? And when we do that, what we find is that the risk of domino effects in the climate system, where the tipping of one element increases the likelihood of tipping of another element, that risk of domino effects increases with global warming. And also the interactions overall lead to more of a destabilization of the climate system. In fact, some of these interactions can effectively lower the critical thresholds for individual tipping elements. And the reason that we have these different uncertainties, that's actually why I came up with the idea of the tipping point model intercomparison project, or TIPMIP, that you've already heard about, with the goal of assessing exactly these kinds of impacts. So the long-term committed impacts, not just for the ice sheets, but for all the tipping elements in the climate system, to further reduce the uncertainty when it comes to the critical thresholds, and also assess the reversibility of impacts. And lastly, to look into the tipping interactions and the potential for tipping cascades or domino effects on the climate system. So if you're interested in this, feel free to either contact me or sign up and show your interest at the webpage. I think we will post the link again in the chat. So we will have an official launch event of the TIPMIP sometime this summer, and we would of course love to interact on this with many of you. And with that, thank you very much for your attention. I'm very much looking forward to the discussion.
Thank you very much, Ricarda. Really nice. Thank you for the nice talk. I think this very nicely complemented the presentation of Sophie, and we are now going to a discussion, in fact, with both speakers at the same time. And while you're free to post additional questions in the Q&A box, I will start with one question for Sophie, and then we will pick from the Q&A box following that. So Sophie, to come back to your talk, can you say a bit more about the different characteristics of the two ice sheets that we heard about, and how does that make them susceptible for different types of responses?
Yeah, thanks, Heiko. That's a great question. So the two ice sheets are very different, but they're very similar and they're very different, right? They're similar in the sense that they're big chunks of ice, okay, that took a long time to grow. Okay, so that's similarity. But they are different in their current settings. And also with the way that, as Ricarda had beautiful photos, images about, the bedrock beneath the ice sheet is really, really important. So for Antarctica, the bedrock gets, especially for West Antarctica, gets very, very much deeper inland. And so it means that, as Ricarda explained, you could have a very strong collapse, and that cannot be stopped. But for Greenland, really, if the ocean, for example, started to cause a retreat, then eventually it would kind of relax, it would kind of retreat into a bed that's kind of not so deep, and therefore it would stop. So for me, really, the main difference for the two ice sheets is really this bedrock and configuration. And therefore, even though both ice sheets could, they both interact with the atmosphere, right? So there could be ice elevation feedback for both of them, or they both interact with the ocean, so the ocean can trigger large retreat and tipping points. Really, for me, for Greenland, the dominant mechanism for triggering a tipping point would be from the atmosphere, and from the Antarctica, it would be the ocean.
Maybe I can just briefly add to that, because as Sophie beautifully explained, the physics for both ice sheets are, of course, that's the same. We have the same processes at play in both ice sheets. What's really different is mainly due to their location and the geometry of the two ice sheets. So Greenland is located much further away from the pole, so it's already warmer around Greenland than in large parts of Antarctica. And that's also why there's this possibility of having surface melt that is reached at lower warming levels than for the Antarctic ice sheet. And also the Greenland ice sheet surface is lower than that of the Antarctic ice sheet in large parts. So again, that leads to differences in the temperature and also in the precipitation for both ice sheets. And then we have those differences in the bedrock topography, and all of this gives rise to actually very complex structures, even though the physics are really the same, and we understand those better and better. But it's really the location and the geometry that gives rise to these very different feedback mechanisms.
Great, thank you for addressing that question. I think that we could also then ask one from the audience, and one of the upvoted questions from Gabrielle refers to a paper that came out in 2018 by Will Steffen, and I think Ricarda, you were also co-author on that. And that paper explored feedbacks and tipping points and the potential for shifting planet into a hothouse Earth state. And so she asked, with greenhouse gas forcing exceeding Pleistocene levels, approaching Pliocene levels. What are the limits to the climate system and implications for the trajectory of the climate system? Absent intervention, is the planet heading to a Miocene state?
Yeah, thanks. Great question. So this question really is about the overall stability of the Earth system as a whole. So with all its interacting parts, including the different tipping elements. And the question here is, what future trajectories are really thinkable when we consider this full stability landscape of the Earth system? And in our thinking, we're very used to thinking of sort of more gradual changes or linear changes, because that's what we used to also from day-to-day life in many aspects. So we could imagine, of course, a world where the difference between 1 and 2 degrees of global warming leads to the same amount of impacts or kinds of impact as the difference between 2 and 3 degrees of warming. But as we know, it's not like that. These impacts actually increase with warming, and we have also a lot of non-linearities in the system. And so it is also thinkable that there is such a thing as the hothouse Earth state. That means a state that is considerably warmer than today's Earth system state. And we've already seen, we already have temperatures that have risen much faster than in human history altogether. So we're already in uncharted territory, so to say. So the question is, could such a hothouse Earth state be one of the future possibilities for the Earth trajectories? And that would mean that all these positive feedbacks interact in a way that really pushes us over the cliff, so to speak, so that we're then in this basin of attraction for such a hothouse Earth state. But to give you an alternative idea, it could also be that we can actually stabilize the Earth system. And that could be, for instance, through all the negative feedbacks that are also at play in the climate system. And to give you an idea of some of the most important negative feedbacks, so dampening feedbacks that currently are still keeping the Earth system stable or resilient. One of them, for instance, is the ocean and the terrestrial uptake of carbon. So right now, we would experience much higher temperatures if the ocean and the vegetation didn't already take up a lot of CO2 from the atmosphere. So that is actually one of those dampening feedbacks that prevents additional warming, or that acts into that direction. Another one is the surface albedo. So a lot of the incoming radiation is already reflected into space, for instance, from ice sheet surfaces and also sea ice surfaces. So all of these are effects that in a way are in our favor, that are keeping the Earth system stable. And so it's not at all clear which of these future trajectories we are on. And it will mainly depend really on our action and the future greenhouse gas emissions, but also other human interferences with the Earth system.
Great, thanks, Ricarda. There's another question that I would like to bring to Sophie from Anthony Joseph. Research indicates that 75 to 100% of extreme melt of 79 Northeast Greenland Glacier is due to atmospheric rivers and föhn wind, so due to extreme events in the atmosphere. Has the IPCC taken this into account in its projections, given the difficulties of predicting atmospheric rivers, and what is the likely synergy between ARs and the jet stream with respect to Greenland ice melt?
Ooh, tricky question. Right. So the IPCC, when we spend the time creating the report, yes, we did consider all the literature that was available at that time. And so we did make an assessment about how well, for example, the climate models were able to capture those kind of short-term extreme events, or those kind of. And so I would have to go back to the report to tell you exactly whether we considered that paper in particular, because there is just so many. But yeah, we did assess some of those. And as you point out, it is very tricky to capture those kind of processes very, very much. But in general, we did note that models are getting much better in general at capturing many behaviors that are important for the ice sheets. So we're getting much better at projecting, for example, surface mass balance. We're getting much better at capturing those other processes that we need. So so therefore, it is a tricky question that I do not know the full answer. But if there was a paper published, then we would have included it. And I don't know what else to be added about from the fact that those new research needs to be included and assessed. The other point I wanted to talk about that I didn't mention, that we, in terms of tipping point, that you might want to kind of consider too for TIPMIP is that we do talk a bit in the AR6 report is surface mass balance and how that's changing in Greenland. And the projections are really starting to change and showing very clearly that, well, indicating that in the coming decades, the surface mass balance is going to possibly reach a tipping point. So as you're having the discussions, how do you define a tipping point and what are the key, which aspect are you considering, and therefore what are the key driver would be a good discussion to have.
Great, thanks, Sophie. So there's been quite a bit of activity on the Miro board, which is also great to see. So I wanted to just take one question from there quickly. And maybe I'll also a caveat that we'll be having another session on oceans and AMOC, but there's one audience member asked, can Greenland melting trigger an AMOC linked tipping point in the North Atlantic, and what is the timeline for that?
Yeah, maybe I can take this one. So yeah, there's a lot of research being done on this interaction between tipping elements, and in particular also those two tipping elements, so the Greenland ice sheet and the AMOC, the Atlantic Meridional Overturning Circulation. And in a way, we here have a positive negative feedback loop. So one accelerating and one dampening feedback. The accelerating feedback is that through ice loss from Greenland and increased melt, which then goes into the North Atlantic, that can lead to a slowdown of the Atlantic Meridional Overturning Circulation. So that can actually increase the likelihood of tipping for the AMOC. But then vice versa, a slowdown of the AMOC can actually lead to regional cooling around Greenland. So not global cooling, but regional cooling around Greenland. So that could be a dampening effect, leading to less melt from the Greenland ice sheet. So this particular feedback loop is really tricky because it actually depends on the timescales that are involved in this accelerating and dampening feedback. And we've done some preliminary simulations on just this with different approaches. And we find that overall, there's a higher likelihood for an acceleration between these two elements. So a higher likelihood for the AMOC to tip if the Greenland ice sheet also tips. But there can, in some cases, be a slowdown of that tipping as well. And that depends on the rate of mass loss from the Greenland ice sheet. So here we have a case of potential rate-induced tipping, where it all depends on how fast the Greenland ice sheet is losing mass, which then gives rise to different stability features for the AMOC. So it's, as you can see, it's a very complex matter, and this one feedback loop already shows that we have these very complex dynamics arising from the different feedbacks. And now you can imagine, if we think of this as a network of many tipping elements, that there are some very interesting stability interdependencies there. Great question, thank you.
Thanks, Ricarda, and also thanks for all the people for asking questions. Here's another one from Bridget Wood. Question for both speakers, but I think this fits very well for Sophie. How close are we to being able to model ice sheet instabilities reliably in global climate models, or is a different modeling approach needed?
Yeah, that's a fantastic question. I'm always amazed by how rapid the development of ice sheet models into climate model is going through right now. It is just totally amazing, this rapid development. And so ice sheet models are being included into climate model dynamically so that they can respond dynamically. And this is really, really important because it allows to capture some of the feedbacks that Ricarda was talking about. And now, the question though is, okay, how reliable, right? That becomes another good question. So by putting ice sheet models into climate models, but when we do this, there are issues that we are facing. The problem, some of the issues that we are facing, for example, is a limitation in computational powers. So for example, an ice sheet model to run and do those instabilities very, very well, for example, to capture very well the grounding line migration, it needs to have very, very small mesh. For example, and that takes a lot of computational power that might be very tricky to have if you're putting into the global climate models. So sometimes the limitation that we are facing right now is no longer in the understanding about how to couple, is simply in the limitations of the actual computer that we are having. So I would say, therefore, coming back to, and we have also seen a huge improvement in the last few years of coupling from the atmosphere to the ice sheets. And so the ice sheet atmosphere being able to do something to the ice sheet model, and then the ice sheet model being able to kind of go back and impact the atmosphere. For the ocean, we've seen some progress too in this coupling aspect, but that's still really much harder because the ocean has to go underneath the ice sheets and be able to adjust itself as the ice sheets collapse. So that's something that's much more trickier in order to, right now that we're facing as a community, but there are promising novel new methods. So to come back to the actual question then, how close are we? If you're thinking about a tipping point linked to the atmosphere in Greenland, I think we can absolutely start doing this kind of model. We are, this is being done, and this is quite reliable. For the tipping point linked to triggered by the ocean, that's still, no, not yet there, but increases, getting closer every day, basically. I'm a very much optimistic person. And so, it is amazing the progress that you've seen in the last few years.
Great. So here's one that is a bit about the communication of tipping points, which I think is interesting. For high impact, low likelihood events, the popular press tends to report the high impacts, but not the low likelihood. How could we communicate these type of events better?
So maybe I can start, and then I'm sure Sophie has some thoughts on this as well. I think this is really crucial, the communication around tipping points and tipping elements and abrupt changes and everything that Sophie earlier defined in her talk as well. Because we're facing, I think, two dilemmas. One of them is on the timescales. So a common misconception around tipping points is first of all that it is something in time, where really it's something in the forcing or in the temperature, for instance. So I think that's one of the issues that we have in communicating science around tipping points. And then the other one is that we have also these very long timescales to consider. So as I said earlier, it's really the changes now and in the coming decades that will determine how the ice sheets are changing over centuries or even millennia. And that is something really hard for everyone to map their minds around, that we can change the face of the planet for millennia to come. So I think that's one of the issues, to kind of bring those long timescales into our present day thinking, because we need to deal with these kinds of long-term impacts now, because now is when we trigger them. So I think that's one of the main points that I would raise, that the communication around tipping points, where we can, I think, do something on the communication around tipping points. And then the other part that you raised in the question is on how to better communicate that these are high impacts but low likelihoods. And I think here a risk framing is really helpful, because we are used to thinking about high impact, low likelihood events whenever it comes to risks. So think of insurance, for example. We all get insurance against high impact but low likelihood events. And this is something that we have an everyday understanding of. And also, this is an area where we're really used to making decisions given uncertainties. So when it comes to tipping points, we also have to understand that intrinsically, just because these are highly nonlinear dynamics, there will be a lot of uncertainties around tipping points. And this is not something that, I mean, of course, we can do more and more research and we get a better understanding of the processes and the tipping points, but there will always be an uncertainty around that just comes from the fact that these are nonlinear dynamics. And so I think, yeah, thinking about uncertainties in terms of risks might be a good switch in our communication as well.
Thanks, Ricarda. Here's another question for Sophie. What is the uncertainty in the loss due to ocean surface warming, freshwater feedbacks, and ice sheet interactions? Most models use parameterizations and low resolutions, in my opinion.
Yeah, that's a fair comment, that the resolution that is being used, you know, if you think about it, so a typical resolution right now is about 1 degree, which is about 100 kilometers for Greenland, or a bit less. So there are resolution issues. So therefore, I would say that there is a high uncertainty those numbers. There is still a very high uncertainty in those numbers, right? But the one part that I think that we cannot forget to talk a bit, and that's why I'm going to deviate to the question, is that in a way, yeah, that for me also a lot of the high uncertainty is also linked to what future climate we're going to face. That's one thing that we always focus about, given a given model, how uncertain it is, but we kind of ignore the fact that a lot of this, there's also like a high uncertainty about what the future climate will be. And so, and for me, those, those are just as more important. And I'm sorry, Heiko, I didn't capture the whole, your whole question. As I was telling to the panelists, I was sick the last few days, so my brain is not really great. So yeah, I
think you answered to it, Sophie. Thanks a lot.
And I'll keep on digging my hole.
So maybe I'll ask this one. It's from our panelists, so one of the organizers of this event. And I think I've seen also questions in the Q&A that address albedo. And so one question is that, so under a high 8.5 watts per meter squared world, and there'd be an associated large amount of air pollution, what would be the interaction with this particulate matter on ice sheets? And would that be yet another driver of albedo change and melting, especially in Greenland, should human activities continue? Yeah.
So I can start on this. So this is a really important and interesting question as well, which is on the changes that air pollution inflicts on the ice sheets and also among glaciers worldwide as well. Because of course we have the overall warming trend, which leads to changes in the surface albedo itself, but then also because of air pollution and aerosols, we have additional effects on the ice sheet surfaces. And here it's really a matter of the various processes that interact at the ice sheet surface. So you can, for instance, imagine that, of course, if you have a lot of, for instance, dust or aerosols settling on the ice sheet surface, it will be a darker surface, so that could give rise to albedo feedback and potentially lead to more melting. However, a layer of dust can also have an insulating effect, so it can also mean that you actually have less melt at the ice sheet surface. So it really depends on the local conditions, how exactly this plays out. And yeah, these kinds of changes can, for instance, be seen whenever we have also a volcano eruption or something like that, and you see those darker layers at the ice sheet surface. You can see just how different parts of the ice sheets react to that. And I think there's still a lot of research being done on fully understanding the processes and how this plays out then for the overall mass balance. So these are just some thoughts on aerosols or air pollution and ice sheets. But there are many more aspects to be considered that really have to do with the surface mass balance altogether.
Yeah, and that's the question. Those are the type of questions that you really need to have an ice sheet coupled to a climate model. And there's been so much progress in the last few years about trying to do aerosol depositions, and so hopefully that's something that we can get a better feeling. I mean, not a better feeling, but a better able to quantify very soon. I mean, in the next few years. It's really, in a way, that's why ice sheet research is amazing, that you can start looking at those amazing questions.
Along those lines, and maybe a bit technical, from Jeff Ridley, how do you calculate the forced Antarctic ice shelf melt once the grounding line has retreated beyond the bound of the forcing model ocean?
Yeah, if I may, so there are different approaches on how to do that. Of course, if you have a fully coupled ice ocean model, it might be that your ocean model really covers that subshelf cavity as well. In that case, you can just go through direct coupling. But in many coupled models, that is not the case, just because of the resolution or because the ocean model really doesn't cover the ice shelf cavities. And so there have been different approaches on how to bridge this gap between global ocean models and the ice sheet models. One of them is our shelf cavity module PICO, which sits sort of in between the global ocean model and the ice sheet model, and it mimics the overturning circulation that happens in subshelf cavities, for instance, in Antarctica. So we have the ice pump mechanism, and that's something that PICO captures in a first instance. So that leads to this general pattern of higher melt near the grounding line and less melt or even refreezing close to the calving front. So that's one mechanism of how to use input from, in the case of Antarctica, north of the ice shelf boundary, so where the global ocean model still has information available, to then, or where we have observations, to then bridge the gap to the ice sheet and shelf model. But it's just one of many mechanisms, and once the grounding line retreats, in that case, PICO, for instance, would retreat with that grounding line and just keep translating those temperatures and salinities north of the ice shelf front into melt rates. But there are other solutions for this as well, and other approaches.
Great. So this one's another, perhaps a bit of a broad question. So, but I think it's interesting just thinking again about these interactions. And so Hans asked, what is the uncertainty in ice loss due to ocean surface warming, freshwater feedbacks, and ice sheet interactions? And kind of what is the roles of parameterizations and lower resolution models in understanding these interactions?
I think this one may have been asked already. We can say a few more words on this, on uncertainties. I think Sophie made the point already that there's, of course, a lot of uncertainties when it comes to these parameterizations, but also a lot of uncertainty when it comes to the climate forcing itself. And then also, of course, our process understanding and the data that is available. You have to imagine that we still have very little data available, for instance, underneath the ice shelves and also underneath the ice sheet, just because it's really difficult to get to it. Again, there has been a huge advancements have been made over the past years. We have amazing new possibilities to put together data that can then also be used to better understand tipping points and potentially even eventually go into early warning detection of tipping points. But this is very recent, and yeah, it's just amazing to see how much progress is being made also in terms of data and observations.
And I think the one thing I want to build on, Ricarda, about this uncertainties, it's true that one thing that we also forget too is that there are some aspects of ice sheet response that it's very hard to know. So the basal condition, like the sliding, like what's happening beneath the ice sheet, and is the ice frozen or able to slide, and how fast, and what is the best sliding law, right? Those are things that it's really hard to know, because unless you remove the whole ice sheet, right? But you don't want to do that. So you're kind of stuck. And so what was fascinating, for example, for ABRUMIP, that's one of the results I really liked, one of the most, is that it really demonstrated how much of the response and the long-term evolution was really due to the sliding law that the different models actually implemented. So that's another aspect to remember, I guess, in the discussion about tipping points, is those knowns, unknowns, things that you can't control too well, and the process at the base of the ice sheet is definitely one of those.
Thanks, Ricarda and Sophie. There's one question here about the likely largest impact. If all fossil fuels end up eventually burned, temperature rise would be over 5 degrees Celsius. So looks like over, say, 10,000 years, both Greenland and Antarctica would largely melt with 200 feet or so of sea level rise. Agree? Question mark.
Yeah, with these really strong warming scenarios and over these long time scales. And I think this is something that the IPCC assessment also showed, that above these kinds of temperatures, so when it comes to 5 degrees of global warming, it's really likely that we will see parts of both the Greenland and the Antarctic ice sheets collapse. And that would then lead to sustained and also irreversible ice loss from both ice sheets. And that means that we would experience sea level rise on the order of, as I showed in the beginning, the sea level potential. So for Greenland, that would be 7 meters, for the Antarctic ice sheet, several tens of meters for these kinds of temperatures over long time scales. But I think what's important to note is that while we're looking at these very high impact events now, of course, the more likely scenario, and also if we consider the coming decades or centuries, is that we would experience less global sea level rise than that. However, even smaller amounts of sea level rise already lead to impacts around the globe. And I think that's something that we should also mention here, that even with a meter of sea level rise, that would of course lead to impacts like increased storm surges, groundwater solidification, and other impacts directly at the coastlines that really impact our infrastructures, our ecosystems, and humans that live at those coastlines. And a large part of the world population right now lives near the coast. So I think even for smaller sea level rise, we of course need to consider these impacts as well.
Well, maybe I'll just put one more science question in, and then we'll switch over to a talk about TIPMIP, which Heiko and I've been saving. But I see that there's a question again asking about paleoclimate, and so how important is the geological record to contribute to better understand possible future scenarios and tipping points? I think that's a great question.
Sophie, you want to go first? Yeah.
Okay, well, I'm sure both answers will be amazing. For me, the paleo record is very important, right? Because you are learning about how the ice sheet could respond to a given climate or to given change, right? So you have it's a record, and you learn a lot about the system. And so it's super important, and we really need to we learn a lot. Actually, maybe and there's more and more research trying to kind of do this. How do we use more paleoclimate right now to help us inform about the future? Absolutely. The one thing that you should always keep in mind, though, is that, of course, the future condition will be probably very different than what has ever happened in the past, right? And so that's why there is a caveat that, yes, you need to use it, and you can learn a lot, and we use it, and we do, and we will use it more and more to test our models, and all of those. But yes, the fact that maybe the future, the way that we are warming is so much faster compared to anything we've experienced before, and so therefore it becomes this question about whether what we've learned is still fully applicable or not.
Yeah, I completely agree. I mean, these really are unprecedented conditions. I mean, we know, for instance, that the CO2 concentration in the atmosphere hasn't been rising this much for the past 3 million years. So certainly longer than us humans have been around. And so these are conditions that we haven't faced before. Nonetheless, we can learn a lot about the dynamics in the Earth system as a whole, and also particularly for the ice sheets from these paleo records. And yeah, we also see how the ice sheets, how drastically they have changed in the past. So there have been periods with really high melt rates or strong sea level rise. And these help us understand also what might happen in the future. So I think paleo records can particularly help us to understand rates of change. And in the end, it's those rates of change that we need to adapt to. So it certainly makes a difference if we have a meter of sea level rise in 100 years, or if we have that in much shorter timescales. And therefore, in the end, this is what limits our adaptive capacities.
Okay, so Ricarda, we're slowly coming to the end. So here's a question about TIPMIP. Specifically, is TIPMIP aiming to deliver baseline simulations for standalone tipping elements or for coupled tipping elements such as West Antarctic ice sheet, AMOC, Greenland ice sheet? Are the models going to be rather conceptual or of higher complexity? And there's a related question down here which asks about whether TIPMIP will also address social tipping elements. And if you could do that within 2 minutes, that would be great.
I'll try. Many questions, but I'm also happy to answer those offline if you want to contact me about that. So very briefly on the first question, both. So we will basically have 2 phases for the TIPMIP, and the first one will focus more on individual tipping elements. So for instance, looking into the critical thresholds for Greenland and Antarctica, permafrost, or the Amazon, as we've seen in the past parts of the tipping seminar series. But then we will also in a phase 2 look at the interactions using Earth system models and other approaches. And we welcome models of different complexity, but in this first phase, we're really trying to bring together the communities. So for instance, the ice sheet modeling community, the ocean modeling community, and so on, to really focus on individual tipping elements and the thresholds and reversibility. And then on the last question, we're very much interested also in social tipping, and we will actually also have a seminar in this series on social tipping points, or maybe even several seminars later on in the year. So that is very much of interest. But for this first part, for the TIPMIP, we will focus on the biophysical tipping elements. Thanks a lot for the interest and the question.
All right, well, with 4 minutes remaining, I want to start to wrap up and to do so first by giving just an enormous round of applause to our speakers today, Sophie and Ricarda. You gave excellent presentations and you did such a great job fielding all of our questions. So many thanks to you both, and to everyone who is still online for your participation today in the chat and on the Miro board. The Miro board, as a reminder, will remain active for the rest of this week. So feel free to continue interacting, engaging, and commenting there. So for the next webinar in this series, it will focus on oceans, and there will be a talk on AMOC, and it will take place on Friday, February 11th at 13:30 to 15 CET, with speakers Christoph Heinz from the University of Bergen and Stefan Ramstorff from the Potsdam Institute for Climate Impact Research. The link to register can be found in the chat box. And again, if you would like to be involved with IHSMIP and to stay apprised of the conversations that are going around it, please fill out the expression of interest form. The link can also be found in the chat box. So again, thank you. Thank you so much to our speakers and to everyone in attendance today. It was a really excellent time.
Thank you, everyone.
Yeah, thanks everyone. And thank you also to Hannah and Heiko for moderating. It was fantastic. Thank you so much.